Need a copy of the Chapter 5-7 practice packet? Everyone here has a Chapter 5-7 practice packet? All right. So, as a review, what is an explicit formula? And I don't know about you, but over the weekend, I actually heard someone use the phrase explicit and implicit, not in a mathematical context. They were talking about, I think, their emotions. And they were describing that you can make your emotions explicit by saying them, or implicit by being moody, or by the way you're stalking around or behaving. Anyway, what is an explicit formula when it comes to sequences? How about just an example of one? An example of an explicit formula. You can even take it right off the Chapter 5-7 practice packet. Let's go on for us. An explicit formula.
Fibonacci sequence?
Fibonacci sequence is a sequence, and we would have to say how we're generating it, like what formula are we using to generate it. So a sequence is a sequence, like 1, 1, 2, 3, 5. That is the Fibonacci sequence, and it's a sequence of numbers. And what we would need to do now is put a formula of how to generate the sequence. So that's the sequence. And the explicit formula and the recursive formula, those generate a sequence. So, and this is a tricky one because we didn't do an explicit formula for the Fibonacci sequence. So who's an example for an explicit formula? What the heck about you, my friend? You're on the...
No, that's the practice.
All right. Well, but where were the... yeah, we're in the practice packet. Here we are. Or were you not here that day?
No, I wasn't here.
Oh, well done. Okay. Brennan.
A sub n equals 3n minus 1.
Yeah, wonderful. A sub n equals 3n minus 1. This is an explicit formula because you can explicitly solve for any term in the sequence that you like. So if you want the, let's say the 30th term, then you could do that. You could do that immediately right now. You can just calculate it. You plug 30 in for n, and you can immediately calculate the 30th term. So in this particular case, if I plug 30 in for n, 3 times 30 is 90, minus 1 is 89. And that's what makes that type of formula explicit. They're using the word explicit to mean that you can do it now. You can do it immediately. And you don't have to calculate the first, second, third through the 29th term in the middle in order to get to the 30th term. It's very nice. So that's an explicit formula. What's a recursive formula? Thanks, Brandon, by the way. What would be a recursive formula? Just an example of a recursive formula. Go back in your notes to that section where we were doing recursive formulas. How about Abel? A recursive formula? I don't mean to put you on the spot there, Abel. Anyone who has a recursive formula? Yeah. Who is?
A(n).
Yeah, A sub n.
Minus 1.
Uh-huh.
Plus 6.
A sub n minus 1 plus 6? Is that what you said? Yeah, and let's just put the A sub n in front of that. So A sub n is equal to A sub n minus 6. That's a great recursive formula. Because what it states is that if you want the nth term, you actually have to know the term. Oops, I didn't write it down. You actually have to know the term in front of it. So A sub n means the nth term, which means any given term that you're interested in. And it states that if you want the nth term, you'd actually have to know the term right in front of it, the n minus 1 term. So you'd have to know the previous term, and then what you're going to do is subtract 6. So that's a little bit more of a tricky formula. Because you can't just immediately say, hey, what's the 30th term? If you wanted to calculate the 30th term with this recursive formula, you'd have to first know the 29th term, and then subtract 6 from it. But you might not happen to know the 29th term. If you just randomly want to know the 30th term of that sequence, and you don't know the 29th term, well, then you're just stuck. How do you calculate all the way to the 30th term if all you have is a recursive formula? You'd have to know the 29th term, But in order to know the 29th term, you'd have to know the 28th term, and to know that, you'd have to know the 27th term. And you'd have to go all the way back to the beginning where you'd have the first term. So you'd have to start off by somebody telling you a seed number. Somebody would have to seed that sequence by saying, hey, a sub 1 is equal to 10. And then from knowing the first term, then you'd use this recursive formula to say, all right, well, the second term would be the first term minus 6, and then I'd need to calculate the third term, which is the second term minus 6, and then I'd have to know the fourth term, which is the third term minus 6, and so on and so forth, all the way until you get to the 30th term, which is the 29th term minus 6. So a recursive formula is a lot more time-consuming because you can't just skip to a number later in the sequence. You have to know every term in the sequence up until that point. And that was what's going on with the Fibonacci sequence that Xavier mentioned. In the Fibonacci sequence, that is most famously defined recursively, saying that the nth term in that sequence is the previous term plus the previous term. So the nth term is the n minus 1 term, which is previous, plus the n minus 2 term, which is 2 previous. And you have to add those two together. So just like we saw here, 1 plus 1 is 2, then 1 plus 2 is 3, then 2 plus 3 is 5, and 3 plus 5 is 8, if you kept on going. So the Fibonacci sequence is famously defined by a recursive formula. Although there is an explicit formula to define it, but it involves a lot of square roots, and it's fairly complicated. All right, well, that's the difference between an explicit formula and a recursive formula. The explicit formula, you can calculate any term by just plugging that n number into the formula. And the recursive formula, you need a seed number to start the sequence going, and you have to calculate every term to get there. Okay, what about sigma notation? What is sigma notation? What's an example of sigma notation? Flip through your notes. Everybody flip through your. Now I realize maybe 10 of you weren't here on Wednesday because it was the day before Thanksgiving. I'm not sure why you weren't here, but I did record that class. And I am assuming that you all went home over Thanksgiving break and you watched that video. So flip in your notes right now to sigma notation, and give me an example of sigma notation. Everybody in the room should be flipping in their packet very, okay, good, you're there. Good, you flip a couple pages, get to the sigma notation part. Yeah, thank you. Keep flipping. What page number is it? 15. It's page 15, folks. So what's an example of sigma notation? Who will give me an example? You can just say sigma from, let's say, k equals whatever to the top number, and then give me the formula. So, Aaron, give us an example of sigma notation. Go ahead, Aaron. On page 15, any one of those.
K equals 2.
Yeah, k, sigma from k equals 2
5.
up to 5
2k minus.
of 2k minus 2. Okay, great. So this is sigma notation, folks. Sigma is the Greek letter for S. And that sigma, this Greek letter right here, stands for the letter S, and it stands for the word sum, as in when you sum up a bunch of terms. And that's exactly what we're going to do here. We're going to take this explicit formula. Okay, so sigma notation is used with an explicit formula where you can calculate each term. We're going to calculate the second term. We'll go from the second term, the third term, fourth term, up to the fifth term. So we're going from the second term up to the fifth term. We're going to calculate each of those terms and then add them all together. So in sigma notation, if you were to be as explicit as possible, you would go ahead and plug in the second term. So you'd say 2 times 2 minus 2, plus the third term, so 2 times 3 minus 2, plus the fourth term, so 2 times 4 minus 2, plus the fifth term, plus 2 times 5 minus 2. That's what this sigma notation says. It says, write out all the terms from the second term through the fifth term and then add them all together. So I wrote this out very formulaically so that you could actually see what each term looked like. But if you calculated it, this would be 4 minus 2 is 2, and 6 minus 2 is 4, and 8 minus 2 is 6, and 10 minus 2 is 8. So now I can actually see the terms of the sequence. The second term is 2, the third term is 4, the fourth term is 6, the fifth term is 8. And the only thing that we're really adding here is that the sigma letter means add them all up. So we add them all up, 2 and 4 is 6, and 6 is 12, and 8 is 20. And so that's sigma notation. Sigma notation is a way of adding explicit terms in a sequence. So there's sigma notation, adding explicit terms. Okay, so that's sigma notation. How about an arithmetic sequence versus a geometric sequence? What's the difference between those two? What's an arithmetic sequence, first of all? So everybody who just walked in, I hope you all signed in and grabbed a practice test from the shelf. And go ahead and take out your chapter 5-7 packet, and we're all on page, well, let's see, now we're on page, I think, 17. We're all on page 17 now, folks. What's an arithmetic sequence?
Sequence where the common difference is the same?
Yeah, a sequence where the common difference is the same. So a common difference means a number that we're adding over and over and over. Common difference, which we denote by the letter D. So a classic arithmetic sequence would just be counting by, like counting by twos. If I had the sequence 2, 4, 6, 8, 10, we're clearly adding 2 every time. Adding 2, adding 2, adding 2. Or if you counted by fives, like 5, 10, 15, 20, 25, 30, we're also counting by fives. So in the first case, the common difference is 2, and in the second case, the common difference is 5. There's a certain irony here, because what does difference mean?
Subtraction.
It means subtraction. And yet, what are we doing every single time? We're adding. So what's the answer to that little paradox? Why do we call it the common difference if what we're doing is we're adding a number and over and over? Shouldn't we call it the common adder? The common adder number? I mean, what would be another phrase for it? Why do we call it common difference? Yeah, it's the difference between the number, not the one after it. It's the difference between, well, you could say the difference between the number and the number after it. But it's the difference between the number and the number before it, right? Because if you look at the difference between 10 and 8, the difference between 10 and 8 is 2. Technically, in order to subtract, in order to get the number 2, you'd have to do 10 minus 8 is equal to 2, right? If you did 8 minus 10, you'd get negative 2. But the common difference is not negative 2, the common difference is positive 2. So yeah, thank you, Gary, that's perfect. We would call it the common difference because if you want to know what D is, you take any given number and subtract the number right in front of it. And in fact, that's my next question. How do you solve for the common difference in an arithmetic sequence? You take any given number and subtract the number right in front of it. And in fact, we could write that down recursively. We could say that the common difference D is any given term, that's the nth term, minus the term right in front of it. What's the term right in front of it? Yeah, a sub n minus 1. So this is very important for us to know that in order to find the common difference, you can just take any term in the sequence and subtract the number right in front of it, and then I'll tell you the common difference. We're going to do the same thing with the geometric sequence. So what's a geometric sequence? If an arithmetic sequence means you add the same number over and over and over again, what would it be? What's a geometric sequence? Instead of adding the same number over and over and over again, you what do? We introduced it last time. We didn't do any geometric sequences yet. That's what we're doing today. But we did introduce the idea.
So the common ratio is the same.
What's that?
Were the common ratio is the same?
The common ratio is the same. And what does that mean? To go from one term to the next term, what are we doing? Rather than adding the same number, Lucy, we're multiplying the same number over and over again. So a geometric sequence means that you're multiplying the same number over and over and over again. So in this case, if you're just multiplying over and over again, you're not counting by 2s or counting by 5s, you're multiplying by 2s or multiplying by 5s. So if I start with the number 1 and I start doubling it, so 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. You'll notice now that in a geometric sequence, what I'm doing is multiplying by the same number over and over again. It wouldn't make sense to analyze this sequence in terms of adding, because if you were adding, it'd be plus 1 and then plus 2 and then plus 4 and then plus 8 and then plus 16. That would not be a common difference, right? We're not adding the same amount every time. So it wouldn't make any sense to study this sequence as an arithmetic sequence because the number that you're adding changes every time. That would be an uncommon difference, right? That would be an uncommon difference. So instead of treating that as an arithmetic sequence, we treat it as a geometric sequence because then it's obvious that every time you're just multiplying by 2, multiplying by 2, multiplying by 2, every time to get to the next number. Why do we call that geometric? Why is it that we call this one arithmetic and this one is geometric? Any thoughts? Why we use the word arithmetic to mean that we're adding over and over, and geometric to mean that we're multiplying over and over?
Because the first one is just simple arithmetic, like
Yeah, maybe because this one's simple arithmetic.
it's like one number plus another number.
Yeah, maybe because it's so easy, right? Because, I mean, to be fair, arithmetic is all of PEMDAS, and so there's a little irony here. PEMDAS includes addition and subtraction, but it also includes
Everything else.
multiplication. So, I mean, but maybe what they're saying is that it's really basic arithmetic, right? Arithmetic sequence because it's just adding and subtracting. It's the easiest part of PEMDAS. I think that's probably the answer. And then what about geometric? Why are they referring to geometry? What's the deal with geometry? Why would we associate multiplication with geometry?
Because it becomes like two-dimensional. Like it's
Oh yeah, because it does refer to something that is two-dimensional. Because when we multiply, here's one example. Like on a photo, let's say that I had a small right triangle of the size 3, 4, 5. That's a right triangle. It's a Pythagorean triplet with sides 3, 4, 5. If you did 3 squared plus 4 squared, you get 5 squared. So that's a right triangle. And if I want a right triangle that's twice as big, I would simply multiply all the side lengths times, for instance, 2. And then I'd have the right triangle 6, 8, 10. And that's something that you're allowed to do in geometry. If you just take all the sides of one shape and multiply it by a given number, you get a similar shape. This shape is the exact same shape as this one. It's just been made bigger, like a photocopy machine. You can make it bigger by multiplying by a whole number, or you can make it smaller by multiplying by a fraction. So in a geometric sequence, you're multiplying over and over again, which harkens to this idea of taking a shape and either making it larger or making it smaller. Okay, so that's why we call it geometric. Now, how do you find the common ratio of a geometric sequence? How do I know it is that I'm multiplying by 2 over and over again? I mean, I think in this sequence, you just look at it and you're like, you're multiplying by 2. But what would be, like for instance, if I gave you a sequence that was a little less obvious, not that I can, anything I write down right now I think is going to be obvious, like 15, 45, 135, and so on. What's my common ratio now? What am I multiplying by every time? 3. Now, maybe you just knew that because you looked at 15 and 45 and you're like, hey, multiply 15 times 3 and you get 45. But how else could we do it? You know, if you weren't sure right off the top of your head, like what if I gave you a much larger number? Like, let's say 81, 729, and so on. How would you know what you're multiplying by the first number to get the second number? Exactly, you would divide. You'd take any given number and divide it by the number in front of it. Just like with the common difference, you take any given number and subtract the number in front of it. In the common ratio, you take any given number and you divide by the number in front of it. And that will tell you the common ratio that you're multiplying by. That's particularly handy if your sequence is actually a sequence of fractions. What if your sequence was 2/3, comma, and then 6/15, comma, and then let's say 18, 75ths, and so on. Well, my goodness, what's my common ratio now? What am I multiplying by every time to get from one term to the next? 3 what? The numerator, for sure, you're multiplying by 3, and the denominator, you're multiplying by 5. So you're right. In this case, the common ratio is 3/5 because you're multiplying by 3 on top, and you're multiplying by 5 on the bottom. And the other way you can do that is by taking any given fraction and dividing it by the number in front of it. So, for instance, 6/15 divided by 2/3, that's really 6/15 times 3/2, is divided by a fraction is multiplied by the reciprocal. And then I can cancel out some terms, and I multiply and I get 3/5. And sure enough, that is the common ratio, by taking any term and dividing it by the number in front. All right, folks, this is what we did last week. All of these different definitions about sequences. We talked about explicit formulas, implicit formula, or recursive formulas. We talked about sigma notation. We talked about an arithmetic sequence. And today we'll talk about a geometric sequence. Whew. So that was quite the review. That was a lot of different concepts we talked about last time. Again, for any of you who weren't here last week, if you're Thanksgiving, you were so either comatose from eating food that you didn't have a chance to watch the last week's video, or something and you're out of town, I highly recommend you all go back if you missed last week's class and watch the video from Wednesday. That'll fill in a lot of blanks. For today, let's see here. Today's the 27th. So we're going to wrap up the rest of chapter 7 today. And then on Wednesday, we will do our practice test for chapter 5 and 7. Everybody should have now picked up a practice test from the side there. So that is due on Wednesday. Everybody, do you want to write that down right now? Write on your practice test, due on Wednesday, so you know you have 2 days to do it. Remember to get full credit on your practice test, which I want all of you to get. All you have to do is attempt every single problem. If you get the problem wrong, that's okay. I just want you to attempt every single problem and then come to class. I flip through it. I see you tried every problem, and then you'll get full credit. Please come to class with every problem attempted. It just breaks my heart to give someone half credit or no credit because you didn't do it. So please, everyone, finish your practice test by Wednesday. So that's this week. Next week, you'll take a test on chapter 5, and then we'll have a final exam review. So that's next Wednesday. I will give you a practice final before that day. In fact, I'll probably give you a practice final on Wednesday. That way you'll have a good week to look at it. And then we take our final exam, and your course survey is actually online. I'm going to open up your course survey to you on December 6th. So anytime after December 6th, you can go online and take your course survey. You do need to take the course survey before you come in to take the final exam. All right? So for instance, I've given you 5 days there to take the course survey at home. If you come into class on the day of the final exam, I'm going to be able to just look and see who's done it and who hasn't. If you haven't done it yet, I'm going to have maybe an iPad and a computer so that you can just sit down and do the survey right there in class before you take your final exam. But that's a little less convenient, right? You have to log into Canvas and then go to the course and then take the survey. So I recommend you do it at home. All right. Any questions about the upcoming schedule?
Are we going to have to turn in the practice final before we take the final?
Yeah, absolutely. That's the final review, so that's the practice final. So it'll be due that day, just like any other practice test. Yeah, Jose, thanks for asking. Can you believe that we only have 1, 2, 3 weeks left? And that third week, not really. It's just half a week. Yeah, so we only have 2.5 weeks left. It's pretty wild. It's very sad, actually. The end of the semester. So sad. If any of you are feeling very sad, you can come talk to me after class. This is a safe place we can talk about feelings. All right. I do have a joke for you today. Why did the cowboy get a wiener dog? Why did the cowboy get a wiener dog? Ready? I don't think you're ready for this one. He wanted to get a long little doggy. He wanted to get a long little doggy? Yeah. All right, folks. So where were we? Go ahead and turn the page again. What page was this? Is it the next
20.
page?
20.
It's the 20. Page 20, folks. Here we are. Now, did we already do any of these?
No.
Nothing?
No.
Wait, I did.
Which one?
Yeah, we did. We did 82 and 83, at least.
I think we did 82, and in fact, we did 83 as well.
I just said.
Well, we set it up. Okay, well, that's fair. We set it up. If you'd like to see the completion of it, let's go ahead and do it. First, we want to find the sum of all the integers from 65 to 95. So remember, from 65, 66, all the way up to 94, 95, we want to add all those numbers together. And we have a formula. Now, first of all, is this an arithmetic or a geometric sequence? Arithmetic means you're adding by the same number. Geometric means you're multiplying by the same number of numbers. So what is this? This is arithmetic. And what are we adding by every time? 1. We're just adding by 1. So already I know my common difference is 1 because I'm adding by 1. And I know that we can use our formula for the sum of an arithmetic sequence, which is the sum of n terms is n divided by 2 times the first term plus the last term. And remember how this works. You might even prefer to write down the first term plus the last term. That's how that works. So we already know the first term and the last term. The first term is 65, and the last term is 95. And so now all we have to do is n divided by 2. Well, what does n represent? N represents the number of terms in the sequence. How many terms are there in the sequence? So how many numbers are there from 65 to 95?
31.
31. There are 31. Remember last time we said the formula for finding how many terms are in the sequence? The formula is the last term minus the first term plus 1. It's not just 95 minus 65 is 30, because there are actually more than 30 terms there. There's 31 terms. You'd have to count it out to see that. And I don't want to count it out, but I'll give you a simpler one to realize it, and that is, how many numbers are there from 65 to 75? So how many counting numbers are there from 65 to 75? Again, if you just subtracted 75 minus 65, you'd say, oh, they're 10 terms. But they're not 10 terms. It's 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75. So there's actually 11 terms. Wait, did I just?
Wow.
No, yeah. Last minus first plus 1.
Wait, so you count 60?
Well, yeah, you're counting how many terms there are, right? And 65 is the first term. And 75 is the last term. So you definitely include 65 and 75. So that would be 11 terms. So the rule is you do last minus first plus 1. That'll tell you how many terms there are. All right, so how many terms are there? 95 minus 65 is 30 plus 1 is 31. And that would be the sum of all of those terms. So 31 divided by 2 times 65 plus 95. Which is what? 15 and a half times 65 plus 95 is 140.
160.
And what did you get?
160.
160?
No, it's in the number. It's not 140.
Oh, it's not 140. Oh, thank you. That's 160.
You got 2480.
2480?
Yeah.
All right. So had you sat there and taken your calculator and actually typed in 65 plus 66 plus 67, all the way up to plus 95, you should have gotten the answer of 2,480. Did everyone get that? On your calculator? You tried it out? Okay. So how about the next one? A man earned $3,000 the first year he worked. And then if he receives a raise of $600 at the end of each year, what is his salary during the 15th year? Now, on the one hand, I really recommend that you always make these things as concrete as possible. You could literally just write down $3,000 in the first year, and then you know the next year he's making $3,600, and then he's working 15 years. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We want to know how much money he's making in the 15th year. So you could always just sit there and write out all the terms in the sequence. But that would be very time consuming. I doubt anybody wants to do that. And that's why we have the formulas that we do. So our formula for finding the nth term of an arithmetic sequence is the first term plus the common difference times n minus 1. And what we want to find is the 15th term. So what numbers do we plug into that formula? What's our a sub 1?
3,000.
Yeah, the very first term, which is 3,000. So our first term is 3,000. And then what's our common difference? What are we adding every time? 600. So that's 600. And then it's n minus 1. So again, n right now is 15 because I'm asking about the 15th year. So it's going to be 15 minus 1. And this formula actually makes a lot of sense. Because you're taking $3,000 and you're adding 600 to it 14 times. Again, you might think, well, but it's the 15th year. You're going to add 600 15 times. But no, that's not true. You've only added the 600 once. So the second term is the first time you've added 600. So that was once, and then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that last term is the 14th time that you've had a raise of $600. So the formula does make perfect sense. You started out with $3,000 and you've had 14 raises by the 15th year. So then you multiply all that together and what do you get? 55 what?
11.
Was it?
50,000.
50,000 what?
400.
Oh, 50,400.
What? No. No.
Oh, wait.
11,400.
11,400.
Oh, yeah.
Thanks for checking, folks. All right. Well, those two problems were a nice review of arithmetic sequences because we got to see the sum formula, we got to see the nth term formula, and we reviewed how to find how many terms there are in the sequence. So let's see, 84. I think I said that 84 was pretty similar to 83, and it is. Because you can see the population starts at 33,200, and then it decreases by 350 people each year, and how many people live there 15 years later. So I'm not going to do this problem with you. What's the only difference between number 84 and number 3? I'm sorry, 84 and 83.
The numbers get small.
The numbers get smaller, because what's the common difference?
Negative 350.
Negative. Yeah, you're subtracting 350 every time. So it's a negative common difference. Whereas in this problem, it was a positive common difference. Okay, great. And then how about 85? John does 8 push-ups. Oh yeah, we talked about this. 8 push-ups on the first day of a 30-day month, and then increases the number of push-ups by 3 push-ups a day. How many push-ups has he done by the end of the month? Yeah, this is also very similar. The only difference is that the first term is 8, and you're adding by 3 every time, so 8, 11, 14, and so on, all the way up to the end. It's the same setup as the last. I'm still dying to know if this would actually work, if the human is capable of adding 3 push-ups a day. I'm going to have to try it. I'm in disbelief. All right. Well, folks, let's keep on going. And I think now we're starting into geometric sequences. So geometric sequences, we multiply by the same number over and over and over and over again. Now, folks, obviously, there are other types of sequences besides arithmetic and geometric, right? Sequences are not always so easy that you're just adding, or multiplying. You could have a sequence that does a combination of them. It could be that you start with a given number, and first you multiply by 2, and then you add 2. And then you multiply by 2, and then you add 2. And then you multiply by 2, and then you add 2. And if you did have a sequence like that, where you're alternating between adding and multiplying, there's just not a name for that. It's not a strictly arithmetic sequence. It's not a strictly geometric sequence. We would just say that's other. Right? It's just some other type of sequence. And because it's other, we don't have any snazzy formulas for that. It's not like we could use the sum formula of n over 2 times a sub 1 plus a sub n, because it's not strictly an arithmetic sequence. And so you'd have to develop new tools for that. We are covering 2 of the most common types of sequences, which is arithmetic and geometric. And the tools that we're studying only work for arithmetic and geometric. All right, so this one introduces the idea, I think, of a geometric sequence. Bruce, which I'm assuming refers to Bruce who? Oh, Bruce Jennings? Is that what you said? Maybe. Or Bruce who? Oh, Bruce Lee. It could be Bruce Lee. Anybody else? Bruce? Well, that's funny. I first thought of Bruce Wayne, but Bruce Lee is even better. All right, well, Bruce, this could be any one of those Bruce, agrees to work for Jim at a rate of 1 penny on the first day, 2 pennies for the second day, 4 pennies for the third day, 8 pennies on the fourth day, and so on. What will Bruce's daily pay be on day 14? And how much wages will he have at the end of the day? First of all, would any of you agree to do a job for a whole month where you get paid a penny on the first day, and 2 pennies on the second day, and 4 pennies on the next day, and so on? And all they're doing is doubling your amount of pennies. Would anybody take it? Raise your hand if you would take that job. The job is basic. You're just digging ditches in the backyard. You're just digging holes. Would anybody take the job? Nobody?
Yeah,
Oh, yeah, for 1 month. You have to do it for 1 solid month. I would take the job in a heartbeat. I would jump up and down for the job. I would push people out of the way to take that job. Nobody else wants to take the job? Pennies are worthless? Well, how much money would you have on the 30th day? Everybody take your calculator. Take your calculator and take 1 penny. Just type it here. Everybody do the same thing on your calculator, because I'd like to show you how to do this easily and simply. If you take your calculator and type the number 1, enter. Okay, just type 1, enter. Now immediately hit ×2, enter. Now if you're on a different type of phone, like a calculator on your iPhone or something, you might have to do hit 1, enter, then ×2, enter. And now at this point, you're going to start hitting enter, enter. And if you just hit enter, 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 it'll start showing you the sequence. So far, I have 1, 2, 4, 8. That's my 4th day. My 4th day, I'm making 8 cents. So that's my 4th day. I'm going to count up to 30. So my 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So how many pennies am I getting on the 30th day? I'm making 536 million pennies by the 30th day. Now, that's pennies. So how do I get dollars? I'd have to divide by 100 pennies and $1 to find out how many dollars that is. So really, I just moved the decimal twice. And so now I have 709 and 12 cents with 368,000 and 5 million. So by the 30th day, I'm making $5 million.
What?
Yeah, that's how rapidly geometric sequences multiply and become large. Wasn't that shocking? So definitely I'm taking that job. And if anybody offers you that job, you should take it, because multiplying sequences multiply very quickly. After all, what does that graph look like? If you're multiplying by the same number over and over again, your function is y equals 1 times 2 to the x. What does the formula 2 to the x look like? That's an exponential sequence, right? And so it takes off really quickly. All right. So now you all know that if a troll or gnome or Rumpelstiltskin approaches you and offers you this job for 30 days, you're all going to take it. All right. So anyway, now you all know how to solve this problem, right? What are you going to do? Take your calculator, and how many times are you going to hit enter? Up to 14, right? Because you're just going to multiply by 2 over and over and over again. And don't forget to move the decimal so that you're talking about dollars, not pennies. All right, so geometric sequences, how quickly do they get big? Very quickly. They get quickly very big. All right, so let's go ahead and talk about geometric sequences, folks. Go ahead and, do you have to turn the page, or are you already there? All right, so here we go. We have some geometric sequences. It says find the common ratio for the given geometric sequence. First of all, just look at that geometric sequence in number 87. Do you see that the terms are getting big quickly? Yeah. Like you go from a single-digit number to a double digit, and then a triple digit, and then a 4-digit number. What do you think the next number is going to be? Either 4 digits or 5 digits, right? Because it's getting big very quickly. Geometric sequences have that property. The sequences get big very quickly. So what is the common ratio? What are you multiplying by? 4. You can probably see that very easily by looking at 4 to 16. Right? You can just do that in your head. You're like, well, 4 times 4 is 16. So the common ratio is 4. But remember, if you can't tell just by looking, you take any given term and divide it by the term in front of it. And I'd like you to write this formula down. Okay? The common ratio is the nth term divided by the previous term. Right? The common ratio is whatever given term you're looking at, divided by the term in front of it. That's what a sub n minus 1 means. The term in front of it. Where did that formula come from? Well, that formula is fairly intuitive. It just says take the nth term and divide it by the term in front of it. But it comes from the recursive formula. When you do a recursive formula for a geometric sequence, it's simply that the nth term is equal to r times the previous term. If that makes sense. That if you want any given term in the sequence, you take the term in front of it and you multiply it by r. Because that's what you're doing every time. You're multiplying by r to get the next term. So with this formula right here, a sub n is equal to r times a sub n minus 1. If I want to solve for r, I simply divide both sides by a sub n minus 1. And that gives me the formula. That the common ratio is the nth term divided by the term in front of it. So that makes sense. What do you know about the common ratio of a sequence that alternates plus minus plus minus? What must the common ratio be? It must be negative. And you can tell that very quickly by taking any given number and dividing by the number in front of it. The common ratio is 81 divided by negative 27, and you get negative 3. So the common ratio must be negative because the signs are alternating. And what about when you have a fraction? How do you find the common ratio when the terms are all fractions? You could still implement the same strategy, right? You could take any given term and divide it by the term in front of it. So I can take 256 thirds divided by 64 thirds, and then know that dividing by a fraction is the same as multiplying by the reciprocal. So 256 thirds times 3 64ths. And then I cancel the 3's, and 256 over 64, what is that? 4? Yeah, so the common ratio is 4. But another way of doing a common ratio for a fraction is to analyze the numerator and denominator separately. Just analyze them separately. In the numerator, we're multiplying by 4, and in the denominator, we're multiplying by 1. So my common ratio is to multiply by 4 in the numerator and multiply by 1 in the denominator. So my common ratio is 4. You can always look at a fractional sequence and analyze the numerator and denominator separately. Kristen, do you have a question? Oh, okay. All right, and then what about if your sequence has decimals in it? Same thing. To find the common ratio, you take any given term and divide it by the term in front of it. All right, so that's the basics of a geometric sequence, the fact that you're multiplying over and over and over again. So let's go ahead and practice finding some terms in these sequences. I won't do all of these, but I'll do some of them with you. What's that about?
Nothing.
Oh, nothing. Okay. What do you want? Bold? Oh, that's not very nice. Don't be bully. All right. Find the nth term of the geometric sequence. So, folks, you could do this by simply writing it out. So let's analyze the information they've given us here. They've told us that the first term is 5. They've told us that the common ratio is 5, so we're going to multiply by 5 over and over again. And they want us to go out to the 6th term. Actually, what they want is to find the nth term of the geometric sequence. So we could write out all 6 terms. That's what I'm going to do. So we're starting with 5, then 5 times 5 is 25. Times 5 again is 125. Times 5 again is 625. Times 5 again is 3125. And times 5 again, I'm not sure. Who's got that for us? 15,625? All right. So there's our nth term, 15,625. Now that's a technique that always works, right? You can just sit there and multiply out all the terms until you get to the one you want. But that feels a lot like a recursive sequence, where you have to actually sit there and do all of those calculations to get to your term. What if you just want to get to the end? What if you just want to get to that last term? Well, with the arithmetic sequence, remember we had a formula, which is a sub n equals the first term plus the common difference times n minus 1. And that way you can just jump to the nth term. That was arithmetic. And likewise, there is a geometric formula that will let you jump to the end, to jump to whatever term you want. And that formula is a sub n equals the first term times the common ratio to the power of n minus 1. Compare those two formulas and notice that there are some similarities. What's the same about those two formulas? There are some striking similarities. What's the same about them? They both have a simple one. They both require that you start off with the first term. I should have written this right on top of each other. A sub n equals a sub 1 plus. There. Now they're right on top of each other. They both start off with a sub 1, and that makes sense because a sub 1 is essentially your seed number. Right? That's how the sequence gets started. And then what else do they both have? They both have the n minus 1 in the formula. For the geometric sequence, the n minus 1 is the exponent, whereas in the arithmetic sequence, the n minus 1 is a number that you're multiplying by. And what else do they both have? They have the common difference or the common ratio term. So in the arithmetic sequence, you're taking the first term and you're adding the common difference times n minus 1. And in the geometric sequence, you're taking the first term and you're multiplying by the common ratio, which is being raised to the power of n minus 1. So these formulas are very similar. And so if I had wanted to just get the 6th term of this sequence, everyone write it down, you would have said, well, take my formula, which is a sub 1 times r to the n minus 1. And so the 6th term would have been the first term Well, let's plug it all in. The first term is 5, times the common ratio, which is also 5, to the power of the 6th term minus 1. So plugging all this into the formula, it would have been 5 times 5 to the 6 minus 1, which is this absurd-looking 5 times 5 to the 5th. Boy, that's a lot of 5s. Which is really what? 5 times 5, 5 times, and sure enough, 5 times 1, 2, 3, 4, 5 times. And so that's really 5 to the 6th, which is 15,600. So what I'd like you to practice for the next few problems is to practice using our formula. Instead of actually just sitting there and writing out all the terms, which you could do, I doubt you'd want to, because like in the very next problem, we're talking about the 11th term. The 11th term, and as we've already seen, geometric sequences get big very quickly. So you wouldn't actually want to multiply by 3 11 times, because how big do you think your number would be? In the millions? In the billions? In the trillions? Not sure, but it'd be pretty big. So if you did want to start by writing out the sequence, the first term was 2, and then you're multiplying by -3. So 2 times -3 is -6, times -3 is positive 18, times -3 is -48. And that's about as far as I'll go, just to kind of demonstrate what the sequence is looking like. That it's alternating plus minus because the common ratio is negative. And what we really want is the 11th term. So you start by writing down the formula. The nth term is the first term times the common ratio to the power of n minus 1. Plug in all of your values. So my 11th term is the first term 2 times the common ratio of -3 to the power of n minus 1, which is 11 minus 1. Why did I put my common ratio in parentheses? Because it's negative. It's really important. When you plug this into your calculator, you have to be very careful with that negative. So my 11th term is 2 times -3 to the 10th. Which part, according to PEMDAS, should you calculate first? Yeah, the -3 to the 10th. I would type that into my calculator separately. I would do parenthesis -3 to the 10th. And then multiply it times 2 to get your final answer. By the way, folks, in your calculator, can you type in -3 to the 10th? Or should you type in parenthesis -3 to the 10th? This is a very common mistake. Which one can you type in, or can you type in either one? You have to type in the parenthesis. What will this one equal? If you literally type in -3 to the 10th, you'll get the answer -59,049. Whereas if you type it in with parentheses, -3 to the 10th, you'll get +59,049. What's the difference between these two computations? Why is one negative and one positive? Yeah, exactly. Here the negative is actually outside. Technically, you know what this one looks like? This is -1 times 3 to the 10th. That's what this one is. It's since the negative is out front, it's really 3 to the 10th times a -1. And that's completely different from here, which is the negative is on the inside of the exponent being multiplied over and over and over again. See here, you're just multiplying 3 times itself over and over, and 3 times itself those are all positive numbers. 3, 9, 27, 81. And then at the very end, you multiply by -1, which makes the answer negative. Whereas here, you're multiplying a negative times a negative. So the signs alternate back and forth. That would be -3, +9, -27, +81, -7, 29, and so on. And it just so happens that because there were 10 of them, it landed on a positive number. All right. So very important that you type all that in that way. And so what was the answer? 118,098?
Yes.
Yeah. Okay. What makes number 93 tricky? In a fraction. Does it truly make it tricky?
No.
No. It's not any more tricky. Now this one, they only want 4 terms. So if you wanted to, folks, we could actually calculate all 4 terms. And that way you can see what the sequence looks like. The first term is 1792. And then we're going to multiply by a 4th, So you can just go ahead and do that. 1792 times a fourth is 448. Times a fourth, which is 112. Times a fourth again, which is 28. Times a fourth again, which is 7. Times a fourth again, which is 1.75. I got a little carried away. It's just so fun to multiply. So there we go, my first, second, third, fourth term. So that one was not too bad just to calculate all the terms. Had you used the formula, a sub n equals a sub 1 times r to the n minus 1, you get that the fourth term is equal to the first term times the common ratio of a fourth to the n minus 1, which is 3. So 1792 times 1/4 to the third. Folks, how do you type that properly into your calculator? Definitely with parentheses. Yeah, you can never use too many parentheses. It would be 1792 parenthesis 1 divided by 4 parenthesis caret 3. So make sure you use parentheses when you type that in. What could you do instead of 1/4?
0.25.
You just do 0.25, and maybe that would make your calculation easier for you. Another way of looking at this, folks, 1792 times 1/4 cubed. How do you put an exponent on a fraction? Whenever you have a fraction to an exponent, what can you do with that exponent? You can, yeah, distribute it. It's kind of distributing. I would use that word distribute, even though technically it doesn't mean distribute. But yeah, you put the cubed on the numerator and the denominator. So this is really 1792 over 1 times 1 cubed over 4 cubed. And 1 cubed is just 1, so the 1s are gone. And that's really 1792 over 4 cubed. It's just another way of looking at the answer. It's just another way of looking at the answer. And in fact, that's another way of looking at the sequence. The sequence, starting out as 1792, is 1792 over 4, and then 1792 over 4 squared. And then this next term was 1792 over 4 cubed, and so on. So that's just one more way that you could have thought about this sequence, is that because you're multiplying by 1/4 every time, you're really multiplying by an additional 4 in the denominator every time. All right. Well, I'm going to leave you to do number 94. It's a little bit of a challenge. I'd like you to try it. Yeah, just a second. Yeah, we'll better just a second. All right, where are we at then? That was number 94, so number 93. It says find a general term a sub n for the geometric sequence. One's right here, what you're going to try on your own. They're just asking for the formula, right? If they ask for the nth term, that means just write out the formula. Do you want to choose just one of these for us to do as a group? Which one looks the trickiest? 97? 97 looks like a fun one. So all they want is the nth term. When they ask for the nth term, they're asking for the concise formula that we have. So a sub n equal to a sub 1 times r to the n minus 1. And in this case, so the nth term is, the first term is 2, and then r is 2/9 to the n minus 1. That might not look very satisfying. Right? You might look at that and say, oh, that's it? And yeah, that's it. This is now just a formula that you can use, and you would plug in whatever term number you want, like the 13th term. If you wanted the 13th term, you would plug in 13 for n, and so 13 minus 1 is 12. And then you'd compute that on your calculator, and you'd find the 13th term. All right, I'm going to leave the rest of those for you to do. What goes in? All right. Well, now this is very exciting. We've reached the exciting portion. Well, not that it all wasn't exciting. I'm sure that you were all on the edge of your seats until now, but now you're really going to be on the edge of the seat. You're going to fall on the floor. So this next section says that we want to find the sum of the first 5 terms of the geometric sequence. And the first thing I'd like you to do is very carefully write down the sum formula with me. There's a lot of subscripts and superscripts, so let's write this down very carefully together. If you want the sum of the first n terms of a geometric sequence, first of all, it's a big fraction. Oh, perfect timing. It's a big fraction, and in the numerator, actually the denominator is easier, it's just 1 minus r. That's the common ratio, 1 minus r. That's the denominator of our great big fraction. The numerator is the first term, a sub 1, times, in parenthesis, 1 minus r, and r is being raised to the power of n plus 1. So it's 1 minus r, and that r is being raised to the power of n plus. There. We're going to take a break here, but when we come back, we're going to derive this formula and see where it comes from because it's so awesome. And I just want to point out to you so that when you're looking at this formula, you can clearly see you've got a 1 minus r on the top and the bottom. The only difference is that on the top, that r is being raised to the power of n plus 1. It's not the whole fraction being raised to the power of n plus 1. That would be incorrect. It's not 1 minus r being raised to n plus 1. It's 1 minus r being raised to the power of n plus 1. Just r is being raised to the power of n plus 1. And then the whole thing is multiplied by a sub 1. You might be tempted, and this would be wrong, you might be tempted. What might you be tempted to do with the 1 minus r? Cancel it. You might get so excited, you're like, I'm just going to cancel it and get a sub 1 to the power of n plus 1. But that would be super wrong. Why would that be super wrong?
They're not the same.
Yeah, they're not the same. And what does this formula imply you do? You take the first term and you multiply it by itself over and over and over again. That doesn't even make any sense. You know, if the first term is 2, but then you're multiplying times 3, so 2 times 3 is 6, times 3 is 18, times 3 is 48, and I want to add together all these terms, where these terms have been multiplied by 3, it would make no sense at all to simply multiply 2 times itself over and over and over again. So resist that temptation. You cannot cancel the 1 minus r. The formula is a sub 1 times 1 minus r to the n plus 1 over 1 minus r. All right, let's take a break, and then when we come back, we'll derive this formula. The time is 9:02, so let's come back at 9:12.
Hi there, Minkamar. Minkamar, I really like your phone. Because it reminds me of my old iPhone. Because that was a really nice iPhone.
I turned that in.
You emailed it to me, didn't you?
No, I emailed you. They said the extra credit couldn't be turned in late, so I just emailed you the extra credit.
No. We'd have to go back and look at the email. I thought I said you could just turn the extra credit in on Monday. But to go ahead and send me the quiz.
See, I think it was the other way around.
Okay, well, I might have done that. And in any case, I'm going to take it.
Yeah, you did. Okay, I'm sorry, yeah. But I've got it done. It was.
And Evan, you weren't here on Wednesday, right?
No, I wasn't.
And have you already gone and watched the video?
I watched like 30 minutes.
Okay, and you're going to finish the rest?
Yeah, I'll finish it.
All right.
All right, thank you.
Yeah, thank you.
So for these ones, I think use sigma
Why don't they use sigma for the geometric? That's an interesting question.
in the question.
Yeah, why don't they?
Because they can make directions. It says find the sum of the first 5 terms of the geometric sequence. So you could say the same, just say sigma, right?
Mm-hmm. Yeah, you could.
Because they're writing all of that.
Yeah. Yeah, that's a really good question. I don't know why they don't use sigma for geometric sequences. Now, to be fair, I think they do. I think they probably will. Maybe not in this packet, but I mean, I'm sure that they do because sigma is a general expression used for anything, even sequences that aren't arithmetic or geometric. Yeah. But maybe in this particular context, they just do not.
I'm just a big fan of being able to look at something without having directions, being able to solve it.
Without being able to what?
Without the directions, and just being able to like solve it.
Oh,
I'm a big fan of like looking at it. Just being able to.
I feel the same way. I just want to look at it, and I don't want to read the directions because I don't want to be told what to do.
That's exactly what I'm saying. Thank you.
Yeah, well, you know, I identified with that. All right, folks, to see where this formula comes from, because I think looking at this formula doesn't make any sense, like any conceptual sense. Like when you look at it, do you think to yourself, oh yeah, sure, of course, that just, that adds up all the terms. Like it doesn't make too much sense. So what I'd like y'all to do is take out a sheet of lined paper. Do you need lined paper? Where are we, right here? Actually, you can put it down at the bottom. You'll have room down at the bottom. But you won't need the entire bottom, all right? So the entire bottom space. And I'd like to go through this proof with you because it is a classic. This is a definite classic proof. And part of your mathematical cultural education to see where a proof like this comes from. So what I'd like y'all to do first is go ahead and write down, I'd like to find the sum, so S sub n. I'd like to find the sum of the first n terms. So we're going to write down a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 all the way up to a sub n minus 1 plus a sub n. So we're just looking as generally as possible at this idea that I'd like to add up the first n terms in a sequence, and we're calling that S sub n. Now keep in mind now that we're talking about we're talking about a geometric sequence. Because if we were talking about the sum of an arithmetic sequence, we already know how to do that. That's pretty straightforward. We saw the idea of a sub 1 plus a sub 2 plus plus a sub n minus 1 plus a sub n. If this was a arithmetic sequence, you could simply pair up the first plus the last term, the second plus the second to last term, and so on. And each of those pairs would be the same. Remember, if we did 1 plus 2 plus 3 plus plus 98 plus 99 plus 100. See, in the arithmetic case, we were able to simply say, okay, we're just adding 1 every time. So if I take the first and the last term, that's 101. If I take the second and the second to last term, that's also 101. If I take the second to the second to last term, that's also 101. And you keep on pairing up the numbers from the beginning and the end, and you'd have, since there are 100 terms, you'd have 50 pairs of numbers that are all equal to 101. And that's where we got the arithmetic sum formula of n over 2 times a sub 1 plus a sub n. So remember, a sub 1 was the first term, a sub n is the last term, and this formula for the arithmetic sequence had the notion of taking the first term and the last term, 1 plus 100, adding them together to get 101. And you could do that all the way down to the middle. And n over 2 represents how many pairs there are. So since there are 100 terms, there are 50 pairs, and that's what the n over 2 represents. So the n over 2 represented how many pairs there were, and the first plus last represented how much each of those pairs added up to. So that's where that arithmetic sequence formula came from. We cannot just do the same trick here. We cannot do the same trick here. And just to demonstrate that, let's say that I took the sequence of multiplying by 2. So 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. How about if I just did that? Well, 1 plus 64 is 65, and 2 plus 32 is 34, and 4 plus 16 is 20. Obviously, we're not getting the same sum every time. You just can't add the first plus the last term. In a geometric sequence, it's not the same as an arithmetic sequence. So we can't do the same trick like we did for the arithmetic sequence with the geometric sequence, which is immediately why the formula is not the same. Right? The formula is not the same because you can't just do the same trick. So instead, and this is very clever, what we're going to do is rewrite all of this in terms of the common ratio. So now go ahead, everybody, write down the sum of the first n terms is a sub 1. And what is the second term? The second term is simply a sub 1 times r, right? Because if you take the first term to get the second term, you multiply by r. So the second term is actually a sub 1 times r. Well, what's the third term? To get the third term, what do? You take the second term and multiply it by r again. So the third term is a sub 1 r squared. What's the fourth term? How do you get the fourth term? You take the third term and you multiply it times r again. So the fourth term is actually a sub 1 r cubed. And you would just keep doing that. So I'm rewriting the sequence not as a sub 1 plus a sub 2 plus a sub 3, but I'm looking at it in terms of just the first term and the fact that you're multiplying by that common ratio over and over again. So what would the n minus 1th term be? We know that the very last term is a sub 1 times r to the n minus 1. Because that's just the general formula. If you want the nth term, it's a sub 1 times r to the n minus 1. And so what's the term before it? A sub 1 times r to the n minus, it's the one before n minus 1. What's the term just in front of n minus 1?
N minus 2.
N minus 2. So now we have this sequence here, and we'd like to find the sum of it. Well, can we all agree for a moment that that a sub 1 is a little pesky, right? Every single term has a sub 1, doesn't it? So what can we do to the a sub 1? Yeah, we can just factor it out, right? So it's really a sub 1, parenthesis, and now what are we adding together? If you factor an a sub 1 out of a sub 1, you're left with 1. And if you factor an a sub 1 out of a sub 1 r, you have r. And so on and so forth. You have plus r squared, plus r cubed, plus da 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 da, plus r to the n minus 2, plus r to the n minus 1. This is just some formal rewriting. We're taking the sequence that we want to find, we're rewriting it, and so thus far we have that the sum of n terms is equal to the first term times all that. Well, folks, what I'd like us to do, and you might say, well, JW, this is kind of wishful thinking. Well, let's just now, for the time being, ignore the a sub 1. We could always come back and do this whole proof again with the a sub 1. Well, let's just go ahead and pretend that our seed number was just 1. So let's go ahead and just say, what if I just wanted to find the sum of 1 plus r squared plus r cubed, all the way up to r to the n minus 2 plus r to the n minus 1. Because whatever that sum is, I can always just multiply back the a sub 1, and that would give me the sum that I was looking for. So here's the trick. If you want to find out what that all adds up to, everybody ready? Everybody's to hear? Really, truly, everybody's writing this down? At least start now. At least start right here, folks. If you haven't been writing it down already, please start right now by just writing down the sum of these common ratios. So there's a trick, and the trick is what I'm about to show you. Well, how could I find out what all those things add up to? What I'm going to do is do some algebra and multiply both sides times r. What would happen if I multiplied both sides times r? Now on the left-hand side, I simply have r times s of n. And on the right-hand side, what happens when I distribute that r? I distribute r all the way down. What technically happens in there? Yeah, each of these terms get multiplied by r, and what happens to the exponent? They all go up by 1. So now I have r plus r squared plus r cubed plus r to the 4th plus da 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 plus r to the n minus 1 plus r to the n. Well, that formula now looks almost identical to the one before it. And I'm going to go back now and erase the r that I multiplied by so we can see that original sequence that I had. There. So I've got sum of n terms, and I also have that whole sequence multiplied by r. And we can do something right now that's going to very much simplify this, because ultimately what we want to do is solve for s of n. We want to solve for the sum. And we have all these terms over here, which is really distracting. And what would be really nice is if we could get rid of all those terms, somehow cancel them out. And in fact, what we're going to do is now subtract, take the first formula and subtract the second formula. So what happens if I subtract, if I take the whole top formula and I subtract the second formula? Well, on the left-hand side, we simply have s of n minus r s of n. We have those two terms and we subtract them. Well, what happens on the right-hand side when we subtract? We don't want to subtract 1 minus r, because that doesn't really do anything. But what about combining like terms? Could I do r minus r? That'd be 0. And r squared minus r squared would also be 0. And r cubed minus r cubed would also be 0. And so by subtracting these two terms, go ahead. You get to take your pencil and cross out all the terms in the middle, going all the way down to here. The 1 didn't cancel out because there was no number down there to cancel it with. And the r to the n didn't cancel out because there was no r to the n on the top row to cancel with. And what we have left on the right-hand side is 1 minus r to the n. Well, that simplified quite a bit. Through algebraic manipulation, we got rid of all those many terms, all the n terms, and we got it boiled down to just s of n minus r, s of n equals 1 minus r to the n. Our goal all along has been to figure out what the sum of all those n terms was, s of n. Can we now solve for s of n? Sure could. I can factor out an s of n. So s of n outside of 1 minus r equals 1 minus r to n. So I factored out my s of n right here, so I have s of n times 1 minus r equals 1 minus r to the n. And now I can solve for s of n by simply dividing the 1 minus r term. And we've done it. The sum of n terms, and I just realized to my horror that I wrote down the wrong formula on the board. The sum of n terms is 1 minus r to the nth over 1 minus r. Folks, again, to my sheer terror, I wrote down 1 minus r to the n plus 1. It's not n plus 1, it's just n. Now that was the sum of all the terms without the a sub 1. We just did the sum of all the terms without the a sub 1. So now we just go back in and we can say, I want the same term, the same sum, but I want it multiplied by a sub 1, so that's where the a sub 1 comes from. So that's our sum of the first n terms. Did everyone go back and erase the n plus 1, which I had on the screen, which was incorrect? That was a typo. This is our actual sum formula. So for a geometric sequence, the sum of the first n terms is a sub 1 times 1 minus r to the n, all over 1 minus r. Yeah, folks, as I just did that with you, it occurred to me, boy, I might have just lost a bunch of you out of the sheer number of variables that I had up there and how unexciting the variables were. It probably would have been better had I done this with numbers instead of letters. Like, as a for instance, what if I said that I wanted to find the sum of 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. So I'm doing a geometric sequence where I'm multiplying times 2 over and over again. And I want to know, what does all that add up to? Had I taken this and multiplied both sides by 2, then I'd have had 2 times s of n on the left. Then if I multiply all those times 2, I'd get 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. I think with numbers, this would have been a little more clear. Because then now when I subtract these two formulas, what do I have? On the left, I can do s of n minus 2 s of n.
And then on the right-hand side, again, we subtract the 2, the 4, the 8, the 16, the 32, the 64. All those cancel out. And I'm just left with 1 minus 128. And then on the left-hand side, again, I can factor out the n, s sub n. So it's s sub n over 1 times 1 minus 2 equals 1 minus 128. And I divide off the 1 minus 2. And I get the sum of that sequence is 1 minus 128 all over 1 minus 2. That's the manipulation that we were doing. And all that said, maybe you're thinking, oh, okay, well, that's all fine and good. That's where the formula comes from. How do we use the formula? Right? Because that ultimately we just need to know how to use the formula. But that's where the formula came from, and it was a pretty clever idea. It's actually a really clever idea. I want to jump up and down and talk about how clever that idea was, because someone had this formula with a whole bunch of terms being added together, and someone had the idea to multiply that whole long formula times the common ratio, and then subtract those two formulas from each other, because that canceled out all those pesky terms. You know, like let's say there were 100 terms in that sequence. They'd have just canceled out 99 of them and boiled it down to this, which they were then able to manipulate and find the sum of 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 is really 1 minus 28 over 1 minus 2. It was incredibly clever to do that manipulation. All right. So how do we do it? We'll go ahead and do a couple. No, that's no joke. So what does it say? Use the formula for S of n to find the sum of the first 5 terms. So that's all they're asking for is the first 5 terms. So they've already given us 1, 2, 3, 4 terms. It wouldn't be that hard for us to just find the 5th term. What's the common ratio? Times 4. So we know our common ratio is 4. 320 times 4, we can type that into our calculator real quick, is what, 1280? Will someone check me on the calculator? Is the next term 1280? Okay, good. So in this particular case, there's only 5 terms. It'd be very easy just to add these up. You could just take your calculator and add them. But in addition to doing that, let's do the formula. So the sum of the first n terms is the first term times 1 minus r to the n all over 1 minus r. And we'll go ahead and say the first term is 5. 1 minus the common ratio of 4 to the power of n. We're talking about 5 terms, so that's 5. All over 1 minus 4. Now, folks, filling in all those numbers right now, it should feel shocking that that is going to tell us the sum of that sequence. Because first of all, I just add up the sequence, 5 plus 20 plus 80 plus 320 plus 1280. The sum is 1705. So the sum of the first 5 terms is 1705. So I already know it because I just did it. But look at the formula. This is fascinating. The formula, get along with it, Dougie. There we go. So the formula turns out 1 minus 4 to the 5th, which is a negative number, negative 1023, all over 1 minus 4, which is another negative formula. At first glance, does that look like a formula that's about to tell us the sum of all those numbers? Not really. It's a very surprising formula. There's nothing really conceptual about it. Not like this formula. This formula is very conceptual, adding the first plus the last term and finding how many pairs of numbers that was. That was very conceptual. This is not very conceptual at all. And yet, sure enough, when you divide, 1023 is divisible by 3, and a negative divided by a negative is positive, and we get 5 times 341. And when you actually multiply that out, lo and behold, you get 1705. So did the formula work? Yeah. The formula really did add together the first 5 terms of that sequence. And it did it in a very non-conceptual way. That is, it's non-conceptual unless you realize that this is what the formula is doing. The formula is taking the sequence that you want to add up, multiplying that whole sequence times the common ratio, subtracting the 2 formulas in order to cancel out all those terms, which leaves you with just that. And in fact, just to slam the point home, I'd like to do it. right in front of you. Let's say that I wanted to find the sum. Okay, I'm just going to bring this down. No, I'm going to move that. Let's say I wanted to find the sum of 5 plus 20 plus 80 plus 320 plus 1280. What would I do? I want to find that sum. So I multiply through by the common ratio, which is 4. So now I have 4 s of n equals 20 plus 80 plus 320 plus 1280. Plus, I have to do 1280 times 4. Which is 5120. And then I subtract the whole thing, which will cancel out the 20s, the 80s, the 320s, and the 1280s. And now I have s of n minus 4 s of n equals 5 minus 5120. And then I can factor out the s of n from the 1 minus 4. And then divide off the 1 minus 4. And do you see the formula? I would have to clean that up and factor out a 5 on the top. If I factor out a 5 on the top, I have 5 times 1 minus 1024. Wait, did I do that right? Yeah.
Yeah, fine.
Oh, yeah. That should work. Over 1 minus 4. But 1024 is actually 5 times 1 minus 4 to the 5th. All over 1 minus 4. There. So it really is the formula. That really is the formula. If I had wanted to add those numbers together, I'd multiply the whole sequence times the common ratio, subtract them to cancel out all those terms, factor out the s sub n, and then divide that portion off and rewrite it a little bit, and sure enough, that's the formula, which was a sub 1 times 1 minus r to the n all over 1 minus r. So the formula is not obvious like this one, but it does make sense if you manipulate that sequence in the way that it's done. All right, well, I wanted to impress upon you how cool that formula was. I don't know if I succeeded or not. If you're going to walk away from here and say, wow, this formula is cool. But it is pretty cool. All right, so how do you apply this formula in the next couple of cases? Like we want to find the sum of this sequence. This is pretty cool because what's happening in this sequence? The signs are alternating. And despite the fact that the signs are alternating, the formula is still going to find out what it adds up to. So I'm going to try just a couple of these with you. So number 100, we want to use the sum formula, which is the first term times 1 minus r to the n over 1 minus r. Well, we need to know the first term, which is simply 3. And what's the common ratio?
-3.
And -3, because we're multiplying times not just by 3, but by -3 over and over and over again. So my common ratio is -3. My first term is 3. And we're going to plug that all in to find the sum of the first 5 terms. So the sum of the first 5 terms is the first term, which is 3, times 1 minus. Now here's something very important. That common ratio is a negative number. What do I need to do with it? Yeah, put it in parentheses.
That is 5.
Yeah, the sum of the first 5 terms. Only because the instructions say find the sum of the first 5 terms. So now I've got the 5th over 1 minus -3. Notice how carefully I wrote that down. You really need to use those parentheses in the numerator and the denominator because in this case our common ratio is negative, and that means you're raising a negative number to a power in the top, and in the bottom you're doing 1 minus a negative, so it's a double negative. So what do we have? I would suggest that you just compute -3 to the power of 5. So with your calculator using parentheses, -3 to the power of 5. So that's 1 minus -243. Then on the bottom, 1 minus -3, that's a chop chop, that's 4. So that's another double negative, so chop chop, that's 3 times 244 all over
3 times 244 all over 4.
Which is 180. Did you all get 183? Is that answer correct? Does it make sense that the answer is correct? We can actually check it because the next term is fairly easy to calculate. Negative 81 times 3 is positive 243. And does that make sense that 3 plus negative 9 plus 27 minus 81 plus 243 is a positive 183? Yeah, what do we have more of? We have more positives than we have negatives. So our answer should be positive. Then you can simply add those together, 243 plus 27 plus 3. Which is 273. And then minus the 9 and minus the 81. And sure enough, it's 183. So in this case, the sequence is short enough that you can check your work by just actually adding up the sequence. All right. I'll just do one of the next two with you. Which one do you want to do, 101 or 102? Sure, I mean, they're both fairly similar. In fact, the sequences look very similar. What's the only difference between them? Yeah, they're flipped. These are reciprocals of each other. So we want to find the sum of all of that. And again, it's up to the fifth term. We can go ahead and find the fifth term right now. What is the fifth term? What are you multiplying by on top, and what are you multiplying by on bottom? 4 on top? Yeah, 2 times 4 times 4 times 4, so 128 times 4. So 512. And on bottom, we just have 3. Now, right now, if you wanted to, you could just type all that into your calculator and get an answer. So it'd be so I just went ahead and added them all together. The sum of the first 5 terms is 227 and a third, or 227.3 repeated. So we have the luxury of being able to check our answer. So now let's go ahead and do our formula. We want the sum of the first 5 terms, where in this case we need a sub 1 times 1 minus r to the n all over 1 minus r. So I'll leave that as the formula. So there's our formula, and we want the first 5 terms. What makes this problem tricky? The fractions. Well, so the first term was 2/3. And then in the numerator, we have 1 minus, oh, the common ratio. What is the common ratio?
4.
Is it 4/3?
No, 4.
Yeah, just 4. 4 over 1 or just 4, right? Because on top, we're multiplying by 4, whereas on bottom, we're just multiplying by 1. So the common ratio is just 4. So we can say 1 minus 4 to the n, which in this case is 5, all over 1 minus 4. So what do we get? 1 minus 4 to the 5th. That's 2/3 times negative 1,023 all over negative 3. What do you notice about this formula? Does anything ring a bell or look familiar? Writing down negative 1023 divided by negative 3. That's what we ended up with from the structure of number 99. Why is it that both of these problems ended up with the negative 1023 divided by negative 3? What about these two problems generated those numbers?
They both have the same combination.
And they both had the same common ratio. The 1 minus r to the n over 1 minus r component was the same because the common ratio is the same. The only difference between these two sequences is the first term. So fundamentally, the sequences both have a common ratio of 4, so we're calculating the same main component of the formula. It just depends on what your first term was, the seed term, the term that started off the sequence. Okay, so 1023 divided by 3, that gives us 2/3 of 341, which is 227.3 repeated. And that's what it actually was when we actually just add them together. Now, it just occurred to me that between 101 and 102, we just did the easy one. Why do I say that we just did the easy one? Because they look fairly similar.
The common ratio is
The
over
ratio is just 4 to that one up there.
Yeah, exactly. The ratio for this one down here, you're multiplying by 1 on top, but you're multiplying by 4 on bottom. So in this case, the common ratio is 1/4. That will change quite a bit about the formula and how we compute it. So we already know the next term is 3 over 512, because it's just the reciprocal of that one. And you could just take your calculator and sit there and add them all up and get your answer. But since this one is a little more tricky, I don't mind doing it with you. We want to find the sum of the first n terms of a sub 1, 1 minus r to the n, over 1 minus r. Now, folks, there's two different ways you can approach this problem. Because the common ratio is 1/4, instead of writing 1/4, what could you write? You just do 0.25, and you plug and chug your way through the problem. And that would be just fine. So, for instance, if you just wanted to use 0.25, you could say the first term was 3/2, and what's 3/2 as a decimal? Yeah, you could just say 1.5 times 1 minus 0.25 to the 5th, all over 1 minus 0.25. And that'd be pretty straightforward and simple. You just have a bunch of decimals. You can type them all into your calculator. And so I'll go ahead and do that. 0.25 to the power of 5. Whew, actually, that's pretty miserable. Everybody go ahead and type in 0.25 to the power of 5 in your calculator. What do you get? Yeah, it appears to be a big number, but that's ironic. Is it really a big number? Yeah, it's 9 point. What your calculator says is 9.765625 e negative 4. What does that e mean?
Move the decimal over.
Yeah, that's scientific notation. It really means 9.765625 times 10 to the negative 4. So that's scientific notation. Folks, when you get e on your calculator, you have to pay close attention. That's scientific notation. And that negative 4, the power on the 10 tells you which way to move the decimal. So if it's a positive number, you move the decimal that many places to the right. And if it's a negative number, you move it that many places to the left. So I'm going to take my decimal point right now and move it, and you have to draw little swoops. 1, 2, 3, 4 swoops to the left. So now my decimal's way over there. And inside each swoop, what do I put? What number do I put inside of each little swoopy? 0. So that's really the number 0.000976565. Whew. So using decimals, 0.000976565. Even using decimals, we're left with quite a bit of a calculation to do, which you need to be very careful about doing. So now I'll do the 1 minus that. And that gives me 1.5 times 0.999023475, all over 0.75. How many of those decimals do I need to keep? How many decimals should I be keeping?
All of them.
All of them. Always all of them. Keep all of them. So now I can finally just multiply times 1.5 and then divide by 0.75. And I get the answer of 1.998046. Now at this point I can probably round. But it's infinite, right? Because now I'm at the end of the problem. I could round, but that technically is the sum. Could we check our answer?
Sure.
Yeah, we can check our answer. You could just take the original problem and type it directly into your calculator. You can type in 3 divided by 2 plus 3 divided by 8 plus 3 divided by 32 plus 3 divided by 128 plus 3 divided by 512. And I get the exact same answer, 1.998046875. Is that the same answer, 1.998046875? Yeah. You get the same answer.
Now, when you take the test on this a week from today, can you just write this down? Would your answer be correct? Your answer would be correct. But I would like to see you use the formula. I would like to see you use the formula in doing this. Because even though these problems are easy because it's only 5 terms, what if I had said 50 terms? If I said find the sum of the first 50 terms, could you just sit there with your calculator and type in the first 50?
Yeah.
Sure you could. Nobody wants to do that. Unless you're getting paid a penny a day and then 2 cents on the next day and 4 cents the next day. Then that might be worth your time. But I would want to see you use the formula. All right? So that's how you find the sum of a geometric sequence. Oh boy. I sent that whole thing up by saying that you could just do decimals. If you didn't do decimals, what would you have to do? You would do fractions the whole way through. I don't think it'd be worth it to do fractions all the way through. I mean, you certainly can. But in this day and age, when you have calculators, if you just want to do decimals, that's just fine. All right, folks. Let me turn the page. And is this the last page of our packet? Oh boy, oh boy. Folks, I feel like I approached the sum formula so matrix that I've been able to catch that. I'm referring to matrix and counter read. Okay, I'm going to fix my mistake on this page, and we're going to approach it the right way. I started the previous formula by writing everything out so formulaic with variables. And that's not a conceptual intuitive approach. So let's try this again. You have space down at the bottom, right?
Wait, what?
Yeah. Here we are. Okay, we're going to try the same thing but different. Down here at the bottom, I want to introduce to you the formula for an infinite sum. All right, this is very interesting. An infinite sum. So before we do, let me just remind you that the other day I asked you what was the sum of 1/2 plus 1/4 plus 1/8 plus the 16th plus the 32nd plus the 64th all the way up to infinity. So what was that answer? If you add 1/2 plus 1/4 plus 1/8, what was the answer? Now, this again, just for the people who were actually here on Wednesday. If you weren't here on Wednesday, you have to watch the video at the beginning. But what is 1/2 plus 1/4 plus 1/8 and so on? And I'm going to do it with you on this Desmos. Folks, take a look. Desmos, can you all see it up there? I'm going to turn up the light. Desmos has a really cool feature. Look down here at the bottom where it says functions. You click on functions, and you go to miscellaneous. What button do they have? They have sigma. This is really cool. They will actually calculate a sum for you. So take a look up here. Now I have a formula, and what I want to do is 1/2 to the power of x, or no, n. Right? So I'm going to each term is 1/2, and then 1/2 squared, and then 1/2 to the third, and 1/2 to the fourth. That's going to give me the sequence 1/2 plus 1/4 plus 1/8 plus a 16th, and so on. So I'm going to start with 1, and I'm just going to do the first term. All right? If I just add the sequence 1/2, the answer is 1/2. And can you all see up there that it gives the answer of 0.5? Do you all see it right here? Okay, well, what if I do the sequence through 2? That's 1/2 plus 1/4. So that tells me the answer is 0.75. What if I do the sequence through 3 terms? That's 1/2 plus 1/4 plus an 8. Now the answer is 0.875. What if I go through 4 terms? That's 1/2 plus 1/4 plus an 8 plus a 16th. Now we're at 0.9375. Now I won't keep doing laboring this. What if I do 10 terms? The first 10 terms of this sequence adds up to 0.9990234. What if I do the first 20 terms of that sequence? That adds up to 0.99999046326. What if I do the first 40 terms? Whoa, the answer is 0.99999. What if I do the first 50 terms? Oh, what happened?
Just gave up.
It sure did just give up, folks. Right? Didn't that computer just give up? Because if I add up the first 50 terms, does it actually equal 1?
Yes.
The first 50 terms.
Yes. That's what we learned.
Well, apparently, yeah. I mean, Desmos says so. If I added up the first 50 terms, the sum of the first 50 terms, and you actually did it, it would probably be 0.9999999. Quite a while until you get to something like 8 over 3. Right? So no matter how many terms I add up, the sum is approaching 0.9999999. And what did we learn that 0.99999 is equal to? Yeah, if you really do have 0.999 repeating, that really is equal to 1. We did this result in last class. So that might still seem a little unbelievable that 0.9999 is truly equal to 1, because that means on the number line, when you look at the number 1, there's also another number there called 0.999 repeating. Right? 1 and 0.999 repeating are the same spot on the number line. Okay. Okay, so all that said, we want to talk about adding together an infinite sum. And we have 2 results that we know. One is that if you add a half plus 4th plus an 8th plus 16th all the way up to infinity, that adds up to 1. And the other result we know is that 0.999 is also equal to 1. So I'd like to show you how we can get those results using geometric sequences. So this is what we're all going to do on the bottom of your page. Everybody go down to the bottom of your page and go ahead and write out the sequence S sub infinity equals, we're going to do got 1 plus half plus a 4th plus an 8th plus a 16th plus dot, 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 dot. We'd like to understand this sum. Now, I know I just tacked a 1 on there, and that's just because I want to start it as a whole number. Since we already know that 1/2 plus a 4th plus an 8th plus 16th is equal to 1, what is 1 plus all of that? It should equal 2, right? So we know that all of this should equal 2, because I've got a 1 here, and then the rest of the sequence is equal to 1. So 1 plus 1 is 2. So I know that it should equal 2. That's what we know ahead of time. But what we'd really like to do right now is explore, how can we prove that absolutely? How can we prove it absolutely? And just to remind you of what we did last time, I said, what is 0.99999 equal to? And we did a nice little algebraic proof. I said, well, we're not sure what this is equal to, so set it equal to x, and then multiply both sides times 10, and then subtract. Well, actually, I'm going to put the x down here. And then subtract the 2 sequences. Do you remember what happened when we subtracted? We got the 9x over here. All these 9's canceled out, and we got 9. And then we divide off the 9, and we got x equals 1. So that was the proof we did last time to prove that 0.99999 really is equal to 1. And you'll notice, what did we do? We took our original sequence and multiplied both sides by 10. And then we subtracted those 2 formulas in order to solve for x. And that's exactly what we're going to do here. We're going to take both sides of this expression and multiply by what? We want to multiply by the common ratio, which is 1/2. So if I multiply this side of the formula times 1/2, I get 1/2 times s sub infinity. By the way, what does s sub infinity mean? We're adding up how many terms? All infinitely many terms. So I multiply this side times 1/2, and over here, I'm going to multiply this side times 1/2. And what happens when I multiply all those terms times 1/2? Yeah, I get 1/2 of 1, which is 1/2, and 1/2 of the 1/2, which is a 4th, and 1/2 of a 4th, which is an 8th, and 1/2 of an 8th, which is a 16th, and 1/2 of a 16th, which is a 32nd, and we keep on doing that forever. So we started off by asking a question. We said, hey, what is the sum of all infinitely many terms? And then I took that equation
and I multiplied both sides times a half. So now I have half times s sub infinity equals that sequence. But what do we do now?
No, subtract the two.
Let's subtract the two equations. That was the clever idea that some mathematician had a few hundred years ago to get rid of all those infinitely many terms. We don't want to actually add together infinitely many terms. So the clever idea is to cancel them out. And so if we subtract the top equation minus the bottom equation, on the left-hand side, you have s sub infinity minus 1/2 of s sub infinity. And on the right-hand side, you can cancel out all the common terms, because a half minus a half is nothing, and a fourth minus a fourth is nothing, and an eighth minus an eighth is nothing, and a 16th minus 16th is nothing. And how far does the cancellation go? How far can we keep canceling?
Forever.
Forever. Right? All infinitely many terms now are going to be canceled out. What's the only term that remains on the right-hand side? Just the 1. So now, here on the left, we can factor out the s sub infinity, which is 1 minus a half, is 1. And we can divide over the 1 minus a half. And before we simplify that, just notice the structure of the formula. 1 over 1 minus a half. Where did those numbers come from? Specifically, where did the 1 come from? What was the 1 in the original formula? The 1 was the first term. And where did the 1/2 come from? You could say this is the second term. But more specifically, what was the 1/2?
Common ratio.
The common ratio. And so what is the sum of an infinite sequence? A sub 1 over 1 minus r. That's it. That's the formula. The formula for an infinite sequence, if you're going to add together infinitely many terms, the formula is 1 over 1 minus r. And in this particular case, if we finish the problem, 1 minus a half is a half. And what's 1 divided by a half? That's really 1 divided by a half, which is really 1 times 2 over 1, which is 2. And that's the result we expected. If we added together that original sequence, we figured that it should equal 2. And it does. So this is our formula for the last page. Isn't that nicer than the previous formula? Oh, wait, I wrote that down wrong. It's not 1. A sub 1 over 1 minus r. What's the difference between this formula and the sum of n terms, which is a sub 1, 1 minus r to the n, all over 1 minus r? What's the difference between a finite sum, a finite sequence, and an infinite sequence? What's the difference between the formulas? What do they both have? They both have the a sub 1, and they both have the denominator of 1 minus r. This one has the 1 minus r to the n, and this one doesn't. I wonder why not. What does 1 minus r to the n become if it's 1 minus r to the infinity? This is very casual language. What's r to the power of infinity? What happens if you take r, which is a fraction, like 1/2? What happens if you multiply half times itself infinitely many times? And I'll just, where's the calculator? Google calculator. What happens if you do 0.5 times 0.5 times 0.5 infinitely many times in a row? Oh, no, I have to actually do it. Oh, it doesn't iterate. Oh. What happens if I keep multiplying times 0.5? Infinitely many times in a row. What does the number approach? Yeah, exactly. It approaches 0. And so if you're multiplying a number times itself infinitely many times, what then does this formula become? 1 minus r to the infinity is really 1 minus 0, which is really 1. And so this whole part just goes away, and you're just left with the result of the formula, which is a sub 1 over 1 minus r. So that's how we add up an infinite sequence. There we go. So using this formula, could we confirm the formula for 0.9999999? Let's do that real quick before we actually try these problems. What is 0.99999 as a sequence? This is a little tricky. What is 0.999 as a sequence? It's actually 0.9 plus 0.09 plus 0.009 plus 0009. Does that make sense? The number 0.99999 is really 0.9 plus 0.09 plus 0.009 plus 0.009. And then this is really 9/10 plus 9/100 plus 9/1000 plus 9/10,000. And so what's our first term? 9/10. What's our common ratio? What are we multiplying by every time? Multiplying by 1/10, right? Because on the top, we're not multiplying by anything, we're multiplying by 1. And on the bottom, we're multiplying by 10. So the common ratio is 1/10. The first term is 9/10. Let's see what the formula says. If I add up these terms, which is really equal to 0.99999, the first term over 1 minus r, the first term was 9/10. And what's the common ratio of 1/10? What's 1 minus a 10? Yeah, 1 minus 1/10 is 9/10. And what's 9/10 divided by 9/10? 1. So even this formula agrees that 0.99999 is really equal to 1. Which is pretty fun. All right, well, I've shown you a lot of background about this particular formula. Let's go ahead and apply it. Did you all already write down the formula up there? The sum of an infinite sequence is a1 over 1 minus r. Why did I write this part down? Provided that r is between 1 and -1. Go and write that down, provided that r is between 1 and -1, which on a number line means that your r value has to be somewhere in this region, such as 1/2. So r could be equal to 1/2, or 1/10. R could be equal to 1/10. Why do we have to restrict that the common ratio is a decimal smaller than 1?
If you have a negative.
What's that?
If you're gonna have a negative.
Well, you're allowed to have a negative in the denominator, especially if r is -1/2.
Well, after you.
Oh, actually, when you do that, then you would have a positive. Ah, I see what you're saying. 1 minus -1/2 is 1 plus 1/2, which is 3/2, and 1 minus 1/2 is positive. So, okay, you're right, Xavier. That certainly does restrict that the denominator will be positive. That's true. Well, look again over here, folks. This sum, 1/2 plus 1/4 plus 1/8, that did add up to 0.9999999, right? What if we had just done the sum of, if it was sum of 1 plus 2 plus 4 plus 8 plus 16? What is that sequence approaching? What's 1 plus 2 plus 4 plus 8? What is it, Evan? That's just infinity. That doesn't approach one particular number. And in fact, if I use the formula right now, would the formula work? What's the sum of a sub 1 over 1 minus r? What's the first term? 1. And the common ratio, we're multiplying by 2. 1 minus 2, that's 1 over -1 equals -1. Did that formula really add up to -1? No, that would be absurd. 1 plus 2 plus 4 plus 16 plus 32. Obviously, the number is getting very, very, very big. And for it to add up to -1, well, that's a good chuckle. That didn't work at all. So why didn't the formula work? Because this sequence is not getting smaller and smaller and smaller. The terms themselves have to be getting smaller and smaller so that they actually add up to a finite number. If the numbers are getting bigger and bigger and bigger, obviously they're going to keep on adding up to infinity. So the sequence, the terms themselves have to be getting smaller and smaller and smaller. And the only way for terms to get smaller and smaller is if you're multiplying times a common ratio that is a fraction. It has to be a genuine fraction. So we say that the common ratio, R, has to be a genuine fraction. It doesn't matter if the fraction is positive or negative, but it has to be a genuine fraction so that each term in the sequence is genuinely getting smaller. Do you see how, like in this sequence, each term is genuinely becoming smaller? And that way, when you add it all up, it'll actually add up to one number, not infinity. Okay, so let's try a few. How about that first one? Is each term of the sequence becoming genuinely smaller? It goes 10, 4, 8/5, which is really 1.6, and then 16 25ths, which is really something, 0.64. Are my terms getting smaller? Yeah. Yeah, they sure are. So in this case, the sequence is going to add up to a finite number. And the word we use for that is converge. This sequence is going to converge upon an actual answer. Just like a half plus a fourth plus an eighth added up to 1, it converged to 0.9999, which is really 1. This sequence is also going to converge. Because every number that you're adding to the sequence is smaller than the one before it, it's going to converge to one particular sum. Now, it's not just that the numbers are getting smaller. We need to actually see what the common ratio is. What is the common ratio? How do you find the common ratio again? You take any given number and divide it by the one in front of it. So I'm going to take 4 and divide it by 10. So the common ratio is 4 divided by 10, which is really 0.4. And as a common ratio is 0.4 between 1 and -1? Yeah. So this sequence is genuinely going to converge. If you were to add it up on a calculator, you would see that your answer is getting closer and closer to, let's find out, the sum of this infinite sequence is a sub 1 over 1 minus r. The first term was 10. Common ratio is 0.4. And go ahead and plug that into your calculator very carefully and see what it adds up to. When you type it into your calculator, you have to use parentheses, folks. You have to do 10 divided by parenthesis 1 minus 0.4. If you don't use the parentheses, you'll get the wrong answer. What did you get? Here? Yeah, 16.6 repeated. So does that work? I'd like to show it to you on Desmos again. Here on Desmos, I'm going to add up the first few terms of a sequence where each term is 10 times 0.4 to the power of 10. So, oops. There we go. So if I just do the first term, the answer is 10. But if I add the first, well, I should really change my, there we go. That would be good. Okay. All right, just looking at the first term, the sum is 10, because that first number is 10. And if I add the first two numbers, that's 10 plus 4, that's 14. And if I add the first three numbers, it's 15.6. And watch as I add the fourth term, 16.24. With the fifth term, 16.496. The sixth term, 16.59. And you'll watch now if I just start jumping ahead to the first 10 terms, the answer is 16.6649. If I do the first 20 terms, it's 16.66666434. If I do the first 30 terms, it's already 16.66666. And if I go ahead and do the first 100 terms, or even 1,000 terms, what is the answer? 16.66666 with a 7 at the end, which is just to show that they're rounding. So it really did work. That was the sum. All right, let's try the next one. What do you notice about this next sequence? Yeah, it alternates between plus minus, plus minus. This is called an alternating sequence. And the alternating refers to the fact that you're going plus minus, plus minus, plus minus. And in this case, what's our common ratio? Yeah, negative. We're multiplying. On top, we're multiplying by 1. On bottom, we're multiplying by 5. So the ratio is 1/5. But the fact that it's alternating from plus minus really means that our common ratio is negative 1/5. And so the sum of this, oh, and by the way, is negative 1/5 between 1 and negative 1? Yes. So this sequence also converges. It will actually add up to a specific answer. It's not going to add up to infinity. It's going to add up to one particular number. So our sum of all infinite number of terms is a sub 1 over 1 minus r. The first term was 9, and the common ratio is negative 1/5. So you have a double negative down there. That's 9 divided by 1.2. What did you get? Yeah, 7.5. Of course, this answer is really interesting because it's alternating. You're adding a little, then subtracting a little, then adding a little, then subtracting a little. And if you were to look at a graph of this sum, let's say we're going to graph it, the first value was 9. So for the first term in the sequence, the sum is just 9. But then the next term, we're subtracting 1.4. So the second term, if you add it together, the sum just came down to here. But then you're adding 9/25, which is 0.36. So then my dot goes up a little bit for the third term. That's my sum. And then for the fourth term, I'm subtracting a little bit, so it goes down a little bit. But then my fifth term, I add a little bit, so it goes up a little bit. And what you notice is that it starts out as a ziggity-zaggity, but over time, that ziggity-zaggity doesn't up and down so much, and you end up with a constant sum at the end. Gosh, I wonder if I could graph that. Y equals, ooh, maybe. Y equals the sum? Why not? Let's try it. This sequence is what? It starts at 9, and then it's negative what? Negative 0.2? No, I don't know how to do it. Well done. That didn't make much sense. Well, in any case, the answer, as you plug in higher and higher numbers, the number bounces up and down, and it finally converges upon 7.5. Okay, I heard my phone go off. I know we only have 5, maybe 4 minutes left. Let's look at the last couple. What's the common ratio for this one? What is our common ratio? Analyze the numerator and denominator separately. What are we multiplying by on top? 2. And what are we multiplying by on bottom? 3. So our ratio is 2/3. Is it a positive 2/3 or a negative 2/3? Yeah, because it's not alternating. We're definitely multiplying by 2/3 every time. The whole sequence is negative because your seed number was negative. So our common ratio is 2/3, and therefore, will it converge? Yeah, it will. Okay, let's look at the last one. What's our common ratio for the last one? This one's a little more tricky because it starts with some whole numbers, and it's not quite so obvious what you're multiplying by 4 to get 5. But if you look at the last 2 terms, what are you multiplying by? Yeah, on top you're multiplying by 5, and on bottom you're multiplying by 4. What about 5/4? Will 5/4 converge? No, because 5/4 is really 1.25, which is outside the boundary of this test. We're really multiplying times 1.25. That means every single term is actually getting bigger. Take a look at the decimals. The first term was 4. The next term was 5. The next term was 6.25. The next term was, I don't know, 125 divided by 16. 7.825. 8125. What would you expect this sum to be? 4 plus 5 plus 6 plus 7. If you keep on adding these numbers together, what will you eventually get to? You get to infinity. So this sequence does not converge at all. We call this sequence not convergent, we call it divergent. Like the hit TV show. No, not TV show, the hit movie. Divergent. Wait, what was that movie called? Divergent? Was that what it was? Yeah, Divergent. Obviously, this is a different kind of divergent, right? Divergent meant what? You had to go play in that terrible arena? No, what was it? That's Hunger Games. That's some other movie. What was Divergent?
No, it's the same thing. They were trapped.
Yeah, they were trapped somewhere, I thought. Well,
Yeah.
in any case, clearly this is a different divergence. Divergence simply means that the sum explodes up to infinity. Convergent means that it converges to one number. Divergent means it continues to grow forever. All right, folks, let me see here if I have any announcements for you. I do, real quick. When is your practice test due? Wednesday. So you'll have 2 nights to do it. Although you could have downloaded it a week ago. In any case, you have 2 more nights to finish your practice test. And I think that's it. Some number of you were absent on Wednesday, and you emailed me your quiz from last Wednesday. Thank you for doing that. I received your quiz via email. But if that was you, please now give me your actual quiz. Give me your actual hard copy so I have that as well. Even though you already emailed it to me, please give me your hard copy.